Hi there, guys. You can see it's getting a little darker in here, but it's the same day. I'm about to do 1C. This is 1C from the Oxford HLAA Analysis and Approaches book. Just a word of warning, there is a ton of work in these first exercises. And the exercises are relatively short. And partly that's because they expect you to have some prior knowledge for this. And some people will have done this before already. So for some of you, this is going to require some catching up. And for others, and if you've seen a lot of this before, you can just flick through the examples. You can probably do them yourself without actually waiting for me to do them. Okay, right, well, let's get rid of me, and my pen is now hopefully recharged. And let's just hide this one up. Okay, and here we go. I started talking before, and the video strangely stopped, so we're redoing this. Okay, so we did a bit of this in 1A. And in 1A, we talked about a geometric sequence being something like, I don't know, 1, 2, 4, 8, 16, 32. I don't know if you know what you'd call those things. I would call them the powers of 2. So we go 2 to the 0, 2 to the 1, 2 squared, 2 cubed, and so on. Okay, so this sequence would be, well, this would be if n is equal to an n number at the top, 1, 2, 3, 4, 5. That's meant to be a 3 there. 6. Okay, so this sequence would simply be 2 to the n minus 1. You can see the power is always 1 less than the n number. Okay, and we can also times this by the first number. So in other words, we can scale the whole thing up by starting with, let's say, 3 instead. If we did 3, 6, 12, 24, this would be 3 times 2 to the 2 n minus 1. In other words, the general term for this is un times by the first term, which I call a, they're calling u1, times by r. R is the common ratio. In this case here it's 2. In this case here it's 2. Common ratio you can find by doing the next term divided by the previous term. That will give you your common ratio, what you're timesing by each time to get to the next term, and have n minus 1 in that formula. So that's the formula we're going to be using to start off with. Okay, good. Well, that is done. That is sorted. They come up with a definition saying r can't be equal to 1. Well, it could be, but it'd be pretty boring if you were timesing by 1 every time. So they're saying, well, common ratio is not 1. Otherwise, you constantly get the same term if you're timesing by 1. Can't be 0 because you'll get zeros all the time. Well, it could be, but it would be pretty boring if you kept getting zeros. And neither can it be minus 1. They're not considering that in this case. Minus 1 would kind of oscillate. So think about that one. If you had, I mean, I don't see why it couldn't be minus 1. They're just not allowing it to be minus 1 there itself. So, say for example, you had, I don't know, formula was 2 times minus 1 to the power of minus 1. That would be un. If you, that would just oscillate between 2 times, when you put in 1 there, you'll get 0 here. So to the power of 0 would give you 1. So your first term would give you 2. And your second term, let's just give you a sequence here, give you minus 2, and the next one will be 2, and then give you minus 2. I don't see anything wrong with that sequence. It's just not a particularly interesting sequence. They're also saying we're not allowing you to start with 0. Again, if you start with 0, then anything times by 0 gives you nothing, a whole row of zeros. And again, nothing wrong with that, but it wouldn't be particularly interesting. Okay, then I'm going to skip through some of this stuff here. I'm going to get straight onto the examples. Now, obviously, you might wish to spend a little time reading through things. I suggest it's a good idea to do that. But I'm just trying to get through all of the examples and do a lot of teaching through the examples as we go. Okay, so example 14, it says find the common ratio and write the next 2 terms in each of the sequences. Well, you can see that this one is doubling, so the common ratio is 2, and the next 2 terms are going to be 20 and 40 times by 2. It's very easy to find the common ratio. You do any term divided by the previous term. It will always give you the same ratio, the same common ratio. In this case, your common ratio is a third. You're timesing by a third, or you're dividing by 3. Dividing by 3 is the same as timesing by its reciprocal, timesing by a third. So that's your common ratio. And your next term is going to be a third. And the next one is going to be a ninth. Okay, in this one, it shouldn't matter which one I take. Let's take the third term divided by the second term rather than the second divided by the first. We can see this gives us x squared, 2x squared. So each time we go from one term to the next term, we're timesing by 2x squared there. Okay, so the next term is going to be 8x to the power of 7, and then the next one is going to be 16x to the power of 9. Okay, pretty straightforward. Right, there's 12 of these questions, if only they were all as simple. Okay, right, example 15. Right, write down the number of terms in each of these geometric sequences. Okay, well, again, we're going to use the formula. Now, the last term, 12.15, and we're going to set that equal to A times by R, and R is equal to, what's times by 3 each time there? So times by 3 to the power of n minus 1. Okay, well, how do you solve an equation where your variable is in the exponent? Now, you might know about using logs to solve this, but you're not expected to at the moment. So I think in this case, it's a matter of trial and error. Now, you can actually type this into your TI, Texas Instruments Inspire CX calculator, or whatever calculator you've got should be able to give you a spreadsheet where you can put a formula in at the top. Now you can put, I know with TI Inspire, you can go through the spreadsheets and you can put in a formula at the top column. You need to go through your menus and look for your sequences, putting in a sequence, and it will allow you to put in this thing here. And then it will give you all of your terms of that sequence, and you find out when it hits this number here. If you want to know how to do this with logs, okay, let's do a little bit. So let's just do 12.15 divided by the 0.5 to start off with. It's 81. So we got 81 is 3 to the power, oh, well, I know 3 to the power of 4 is 81. So my n minus 1 has got to be equal to 4, so the answer is 5. Okay, but let's just go through using logs as well. There's two ways of doing it with logs that I can think of, but I'm going to just choose to do this. So if I said 10 cubed is equal to 1,000, an equivalent way of writing that would be to say log to the base of 10 of 1,000 is 3. It's basically saying, what power do I need on 10? Give you the answer of 1,000. What power I need is 3. Okay, so there's a basic example. Now, if I rearrange this in the same way, I'll now get log to the base 3 of 81 gives us our power. Okay, so now you can type that into your calculator, and then that will give you 4. And then you can work out by adding 1 onto both sides, and this is equal to 5. Okay, so that's how you could do it with logs. Logs turn up later in the book, so don't worry about that just yet. Right. Okay, and I mean, you can do a very similar thing for this one here, of course. That doesn't look too pleasant, I have to say. Hopefully that's an exact answer. Should be an exact answer. So again, we've got here 0.429685 is equal to, our common ratio here is a quarter. You can see that from the first one, we're dividing by 4. So we've got 440 times a quarter, or 0.25 minus 1. You can do exactly the same thing as we did in the first question there to get that answer. Okay, right, let's just have a look at that. They've done it using a table. You can do this using a table. You might want to try and do that on your calculator. It's not too difficult. Okay, let's shift on. Let's do example 16. We are cooking on gas here. Let's take this one. Looks like that you're going to use a table for this one as well, but let's see how far we get. So the first term of a geometric sequence is 4. The common ratio is -2. Determine which term has the value of -2048. That seems to be a very similar question to the previous one. First term is 4 times by -2. Remember the brackets? Of course, for example, -2 squared is very different to -2 squared. Right, this one is going to give us 4. This one is going to do the squaring first and then put the minus on the front, give you -4. So remember the brackets, especially with the minuses. And then we've got the n-1 there, and you can do a very similar thing to what you did before. Let's have a little look. Yeah, they've used technology. Okay. Okay, right, example 17. We are really motoring. Okay, example 17. Again, feel free to stop these and have a go at it yourself, or you wait for the answer, or get the answer afterwards. Okay, the fourth term of a geometric sequence is 54. So 54 equals a times r to the n-1, or but 4 would be 3 minus 1 there. That's 4 minus 1, sorry, which is 3. 486 equals 6 times of a times r to the power of 5. Don't really need that times, to be honest, but there. Okay, so we've got to solve these. We've got simultaneous equations here, but probably not like you're used to having them. But instead of adding or subtracting these, to get rid of an a when they're connected by times, you could divide these. So this is the second one, this is the first one. What we'll do is we'll divide the first one, second one by the first one. So 4, quite dark in my room now, 486 divided by 4 is 9. Okay, so if we divide them, we get 9 is equal to, now those are going to cancel. On the left, r squared there. So r is either equal to plus or minus 3. It can't be equal to -3, or can it? Oh, no, it could be, because you could be timesing by -3, and then by -3 again, it would take us back to positive. So both work. Oh, that's interesting. It says determine the possible values of the common ratio. So there we go. Oh, and we're done. Okay, so -3 actually does work as well. Okay, right, next one. Look, 18. We might need to use technology for this one. Just check it out. First term of a geometric sequence is 16, and the common ratio is a half. So we've got 16 times by 0.5 to the power n-1, and we've got 1,000. Just flick it into decimals, and we want to know when is this bigger for the first time. When is this, which of course is equal to our un, when is that bigger than this thing over here? Okay, well, we could try and work out when it's equal, and then we could just take the next term. So I'm expecting that it won't be a whole number when it's equal, so just take the next term. So I'd probably just solve that, to be honest, and then you can use that log technique again. So yeah, remember the log technique. It's, you know, if you remember this, okay, log to the base 10 of 1,000 is 3, then a rearrangement of that, and similarly, you can use a rearrangement of this by saying log to the base of half, or 0.5. Need to divide by the 16 first to get the answer of 1 over 16,000. that would give you your n minus 1. So you can type that into your calculator, add 1, and that's going to be the first term, which equals 0.001 or 1,000th. You want the next term, of course. Now, they've done it using technology. You now know how to use this with, do this with logs. Okay, turns out it's the 15th term. Okay, sum of a geometric sequence. Okay, so this is new and nice, and I'm going to try and do this thing here, this bit here. Okay, I'm going to do that just myself. Okay, so I'll just take a little bit of something, otherwise I can't write on here. So remember we did this in 1b for the sum of an arithmetic sequence or an arithmetic progression. Now we're going to do it for a geometric progression. Now, there's a different trick for this one. Let's just write down what we need. We're saying the first term, the second term, the third term, but the last term on the end. I'm probably not going to give enough space for this. There you go. Okay, all pluses in between because this is a series, and this is the sum of the first n terms. We use the same Sn for geometric sequences as we do with arithmetic sequences. Okay, now this time, instead of writing it back to front, I'm going to times everything by r. So if I times everything by r, I'm going to get, let's type that in here, so we're going to get ar squared plus ar cubed plus, right, and at the end I'm going to get plus ar to the n. If I put another r into n minus 1 lots of r, multiplying together there, then I get n lots of r here. So I'm just increasing the power by 1 if I times by r again. Okay, now again, the trick in this case is to look at the difference between what we have here, because a lot is similar. So all of this could be kind of useful to show you previous term there. Just a moment. A to the r n minus 1, and then the final term is going to be ar to the n. Okay, so you can see that these things are the same. Okay, now the difference between them is this, take away this, if we do it that way around. So what I'm going to do is take the top line off the line underneath. So we're going to say rsn minus sn leaves us with, well, all of this is going to cancel. Okay, and we're going to be left with a r to the n, take away that r. So what to do next? Well, you can perhaps think about that yourself. We want to get Sn on its own. So we'll need to factorize it. And let's factorize out that a as well. Just makes it a little neater. We're getting Sn is equal to a lots of r n minus 1 over r minus 1. Now that's pretty useful if r is bigger than 1. But if r is smaller than 1, a lot of people like to change the formula around. Just use this version of it. So if I times the top by minus 1, if I times the bottom by minus 1, I can switch around the thing inside both of the essentially brackets. Okay, so I can absorb that times by minus 1 into the top bracket, one of the top brackets, of course, this one, and absorb it into this one. Now, if I times the top and bottom by minus 1, I'm essentially doing nothing to it. Doing the same to the top of a fraction, the same to the bottom of the fraction, so it stays the same. So this is just an alternative version. Some people like to use this. Say, for example, if r was a half, then it keeps numbers as positive on the bottom there. So there you go. One thing to say about this, we will deal with a sum to infinity at some points. And the sum to infinity, in the sum to infinity formula, this will disappear. And that's in the cases when r is between minus 1 and 1. So say, for example, if I took 0.5 to the power of infinity, it becomes infinitely small. 0.5 of a half of a half of a half becomes infinitely small pretty quickly after infinite steps. Well, it becomes small very quickly. So this would disappear if r is between minus 1 and 1. that would leave you with this additional formula, A over 1 minus R, and that is called, that's only the sum to infinity. Let's just write this one down. Sum to infinity, in this case here, is going to be A over 1 minus R. Okay, we'll deal with that through the questions as we go through. But this is the proof for the sum. Okay, this above is the proof of the sum, the first n terms of an arithmetic, not an arithmetic, a geometric sequence or geometric progression. Cool, right. Okay, I'm skipping the investigation. You might want to do it. Some of these investigations are really good, in fact. But I'm skipping that because I'm just dealing with questions. I'm not going to use the technology here as well. Although I might do a little bit on Excel about this in a while. You can do all of these on Excel and you set it up really nicely where R is a variable which you can change and get graphs out from it. I might do that in a bit. Okay, example 19. Let's do this. And so geometric series has a first term of 3 and a common ratio of 2. Find the sum of the first 5 terms. Let's look at Sn. Look at A, R to the n minus 1 over R minus 1. And they're saying that first term is 3, so we've put in 3 there. Got 2 is the common ratio, 2 minus 1 on the bottom. And we've got n, and the sum of the first 5 terms, so we're looking for S5. It's 5 minus 1 on the bottom this time. Okay, so it's big minus 1, it's not n minus 1 as the power. Okay, and you can obviously just type that into your calculator and press equals. Next one, that was quick, that's sorted. Look at this, much quicker than I thought today. Okay, calculate the geometric series given by this thing, the summation of I is equal to 1 to 7. 2 times a half to the power of I. Okay, so they want the first 7 of these geometric progression terms added together. Well, let's just see what they are. So let's put in 1 to start off with. So 2 times a half is 1. 2 times a half squared, that's me putting in I is equal to 2 now. So the second term is going to be 2 times a quarter, so that's going to be a half. I can see my common ratio is a half here each time. So my next term is going to be quarter, eighth, 16th, 16th, meant to be an eighth as well, and 32th, and 1 over 64. There we go, we've got 7 terms there. We needed 7 terms. Calculate the geometric series given by this. So we now need to add them all together. That's what it's asking us to do here. Okay, so again, we have A is equal to 1, N is equal to 7, and R is equal to a half. Oh, we're done there, really. We just need to substitute that into the formula. I'm not going to spend time doing that here. It's pretty straightforward how to do that. You can see they've just used the formula again. Okay, next one, example 21. Okay, right, let's have a look at this. Seems to be a bit more involved, the working out here. The first, find 2 possible geometric sequences where the sum of the first 2 terms is 20 and the sum of the first 4 terms is 1,640. Write the general term for each sequence. Okay, well, let's start off by using the formula then. So we want S2 is equal to 20. That's going to give us A, R minus 1. Oh, check that out because R, sorry, just explain that a bit further. That's R to the 2 minus 1. Yeah, sorry, that's right. And then divided by R minus 1 there. Okay, looks to me like the difference of two squares on the top there. You can see that one. Might help out. And we've also got S of 4 is equal to 1640, 1640 is equal to A. And we've got R to the 4 minus 1 and R minus 1 on the bottom there. And I can see actually there's a difference of two squares on the top, but there's not something to cancel with on the bottom. Now, just seeing that, we essentially have two of these. We have these two to solve, two simultaneous equations to solve here. And they're not straightforward, really. We could multiply by R minus 1 on both sides. And we could divide by this, for example, we'll get an expression for A. And we could substitute that in here. And then we could use nsolve on our calculators. And that's probably what I'd do. Probably the quickest way to do it. So nsolve will solve equations for you on your calculator. Go to Scratchpad, go to your menu options, and you've got nsolve there. You can type in your equation, and as long as you've eliminated one of your variables, which is pretty easy to do here, then by substituting in, say, for example, A, by doing a rearrangement there, substituting it into that, then you could set up your nsolve and find your value for R. The problem with that is it will only give you one value for R, and your other one is probably the negative of that. It's a bit far down the line for me to think about just at the moment. Okay, anyway, there's another thing I can see happening here, and that's that this top is also the difference of two squares there. So that could cancel with that on the bottom. So that might make life a little easier, in fact. So we can see that we're getting from here, we're getting if 20 divided by R plus 1 gives us A. Now we can substitute that directly in here. Let's do that. We've got 1640 is equal to 20 over R plus 1 times by, so I could take the A out as a sort of A over 1 if you like, and that's essentially what I'm doing here. So the 20 stays on the top and the R plus 1 becomes the denominator. Oh, and there we go, and we've got R to the 4 minus 1 on the top there. Now that's pretty nice because I've got the difference of two squares on the bottom again. I can see I've got this. These things you kind of have to recognize, and you're expected to be able to do that. And there's a difference of two squares on the top here as well, so we can factorize this. We can have R squared gives us this, and minus 1 squared, all squared gives us minus 1. So this is R squared minus 1, and R squared plus 1 there. So that requires some insight, really, and some good algebraic skills from before. Okay, now we can sort of, get rid of those two expressions there, and we've got a much easier equation now. So we've got 1640 equals 20 times by R squared plus 1, and that's much easier. So we can multiply the brackets, or divide by 20, take away the 1, and take the square root, and we'll take the plus and minus of the square root. Remember, of course, when you get equations like this, say, for example, x squared is equal to 9, then that gives us two possible solutions, plus or minus 3, so plus or minus the square root of 9. But remember, in surds, if we were being asked to simplify the square root of 9, that's simply 3, not plus or minus 3. It's only plus or minus 3 because we're in a situation of an equation, and both of those would work to solve this equation, plus or minus 3. Okay, no, I'm not saying that is the answer. It's just a little point. Okay, then, because I'm running out of space, you can see I'm pretty much there, but let's have a look at what they do. Yeah, they seem to have recognized difference of two squares in both cases. Well, I was feeling kind of clever there. but seems like they've done it in a very brief line as well. Okay, so they've got r is equal to plus or minus 9, and then of course you can go back to one of your original equations there. Okay, once you put in your r value, so let's say, here we go, it was this equation rearranged. Once you put back in your r value, you can find your two values for a, and the question comes together quite nicely then, because you've got a general term, it's going to be a times r minus 1. I don't really need the times, by the way. Okay, so that's going to be your un. Right, good. Okay, so next we've got, I think, 3 more questions to go. Or 4 more questions to go. Yeah, even I'm struggling. Okay, example 22. If you want to go and get yourself a cup of tea, drink of water, or even try the next question yourself, pause me for a bit because I know that I can become quite droning after a while. Okay, example 22. Example 22. The sum of the first n terms of a geometric sequence is given by pen's running out. The sum of the first n terms of a geometric sequence is given by Sn equals 7 to the n minus 1. Find the first term and the common ratio of the sequence. Well, remember, S of 1 is equal to U of 1. And remember, S of 2 is equal to U1 plus U2. So all you need to do in this case is substitute in 1 to get U1. So in that case, U1 is equal to 7 to the 1. Take away 1 is 6. And S2 is going to be 48. So S2, it's just me substituting in 2 into here, of course. So 48, where are we going from there? Find the first term in the common ratio. So that's equal to U1 plus U2. That's 6 plus U2. So U2 is equal to 42. And so the common ratio is always the next term divided by the previous term, which is 7. So there we go. We found the 7 there as well. That's our common ratio. Okay, well, we're still motoring. Let's look at example 23. Okay, right. It says determine how many terms are required for the sum of the geometric series given by this formula here. It's easier for me to say that, to exceed 1000. Okay, so this we can put into our formula, but let's just see what our terms are to start off with. When we put in 1, we get 3 times 2 to the 1. So our first term, U1, is equal to 6. And let's get U2 out as well, just to check what R is, although I can't see what R is. Now we're getting 3 times 2 squared, which is 12. So I can see the common ratio is 2. In fact, the common ratio is hidden in there as well. So our common ratio is 2. So R is equal to 2. So let's set this formula up. We've got S of n is equal to 6 R to the n minus 1 divided by 2 minus 1. Now we can't go and cancel the minus 1 or anything. Nothing to cancel there. We can make it a little simpler by doing 2 minus 1 is just 1. So we've just got this formula here. We could multiply out the brackets if we want. Maybe that's a good idea. Okay, so we've got 6 times by 2 to the n. Obviously, we can't do 6 times 2 is 12. Minus 6. And we want to know when does this exceed 1000. So let's take the 6 across to the other side now. Okay, we've got 1006. And we've got 6 times 2 to the n. Let's just take it over here for a moment. Let's divide by the 6. 2 to the n is greater than 1006 divided by the 6. No, you can use trial and improvement to see when your power of 2 first is bigger, becomes bigger than this number here. Yeah, you can use some trial and error, or you can use the log method, which I mentioned earlier in this video. Phew. Okay, so that's example 23. We're getting there. We really are getting there. Okay, they've done it by using technology, by the way. Again, I've shown you a log method to do this as well. Okay, you obviously, by the way, need an integer there as your final answer. So when you get, is that what I had? 100. Yeah, I just multiplied out my brackets. It was only slightly different, just a slightly different approach. You can see that when you're trying to solve 2n is bigger than 167.6 recurring, you need to go to the next integer answer up from that, of course. So the answer is in between 7 and 8. So you'll need to choose 8. Okay, right. 2 more questions to go. Right, hang in there. Right, 24. Do this. Okay, right. For what values of x does this series converge? Find the sum when x is minus 1.5. Oh, it seems like they're missing something here. Okay, right. For what values of x does this series converge? Now, there's some real thinking behind this, but I think they're going to use technology. Let's have a little look. No, they're not actually. Okay. They seem okay. Let's set it up. Let's take it bit by bit. So let's come up with our terms of this sequence to start off with. So our first term here is putting in 1. We'll get 1 plus x over 2. That's our first term. Second term is going to be 1 plus x over 2 squared. This is really not a classic type of question. So this is really getting you thinking and getting you to do some problem solving with what you understand at the moment. So this is not a standard question from an exam paper. So it's kind of each man for himself, really. Okay, so anyway, this carries on. As we can see, it's going to go up to 1 plus x over 2 cubed and so on. It's going to continue infinitely here. Okay, it says that x is not minus 2. I suppose that's because otherwise, if you put minus 2 in here, minus 2 divided by minus 2 is minus 1, and that makes the entire bracket equal to 0. So you just get lots of zeros. So that's not interesting. Okay, so for what values of x does this thing converge? Now, you can see that it's in the format of a geometric sequence. That's not easy to see. But so, for example, let's look back at our powers of 2. We had 2 to the 0, 2 to the 1, 2 squared, 2 cubed. We had something, the powers, which were increasing. And we have the same thing here. This is our r, right? This is r. So the first term is here, but we're timesing it each time by another 1 plus x over 2. So this is kind of like a hidden geometric sequence in this case, where the first term is the same as the common ratio. And that's hard to spot, I think. So the conditions of convergence were what I talked about earlier. Now, if we take the formula, if we say take this formula again, okay, so a 1 minus r to the n over 1 minus r. Now, again, if we talk about, I don't know, common ratio is equal to 0.09. Now, when we take really large values, let's say to the power of 100, this becomes really, really insignificant, very extremely small. And so this will tend to 0. Now, that's the case as long as r is less than 1 and bigger than minus 1. Okay, But as soon as we go above that, if we say 1.1 power of 100, that gets larger. If we keep timesing by 1, if we do 1 to the power of 100, okay, we're going to get 1 at the end. So that's going to stay the same. So we need the common ratio. We need the common ratio. So let's just write it here to be between, say, the modulus, the absolute value. We're saying there is, forget about it being, let's take just the size of this thing. Let's forget about it being positive or negative. It's got to be less than 1. What that means, by the way, is this. We're saying that r is between -1 and 1. It's saying if you take the positive of r, okay, so for example, -2, the positive of that is 2, the modulus of that is 2. Whereas if we said modulus of 2 is 2 still, okay, so that's what modulus is doing, or what we call the absolute value as well. Okay, so the modulus of r is less than 1 is the same as saying this. Okay, because if you take the modulus of minus 0.99, it still gives us 0.99. Okay, so if r, the modulus of r, if the magnitude of the number, to the back, magnitude of the number is, forget about it having a minus on the front. If the magnitude of the number is less than 1, then you can say that the sum to infinity is equal to a over 1 minus r. In other words, this disappears. Okay, so in those cases, when this disappears, it disappears because your terms are getting smaller. If you're timesing by 0.9 each time, your terms are getting smaller, or at least the magnitude of them, the size of your terms, forgetting about the plus or the minus, it's getting smaller. Okay, so just take that for a second. So that's just the normal sum of n. So, but if r is greater, the magnitude of r is greater than 1, then your terms will be getting bigger. So your terms will diverge. But if terms get smaller, then your terms will converge. Okay, well, I think that's a fact that you're going to have to take on board just for the moment. At the end of this, I'll do a little Excel spreadsheet, and that might make it a little clearer as well. Okay, so let's just look at how they're doing things here. Identify R. So U1 is the same as R. That's what we got to in our working out, is 1 plus x over 2. Right. For convergence, they're saying this. Exactly what I was just saying there. Now they're just sort of coming up with that, which is kind of frustrating. Okay, but anyway, let's go with it. Okay, so we now need to say, well, the magnitude of R needs to be less than 1. Okay, and then all of your terms become, you know, kind of insignificant. And when you start adding extremely small values, they become insignificant. And we have a sum to infinity. That's what we're talking about. Okay, so we've got 1 plus x over 2 is between -1 and 1. Now we can solve that by splitting this up into 2 parts and solving the 2 inequalities. Or in fact, in this version, we can just do things to all sides. So for this one, we can kind of cheat and we can just say take away 1 from everything. X over 2 and 0, and then times everything by 2. If you times everything by 2, you're going to get -4x and 0. So there we go. This will converge if we're between -4 and 0. Okay, then it says find the sum when x is equal to -1.5. Well, that's going to be pretty straightforward because we can then use our sum to infinity. Okay, the sum to infinity is going to be equal to a, and a is going to be 1 plus x over 2. That's -1.5 over 2 divided by, let me just put in 1 minus r, 1 minus this thing here. R is the same as A in this case. So we can just type this into our calculator essentially. So I'm going to leave it as R there because I'm getting a little bored. Okay, you can work it out, right? So they're just substituting it in. And if you're not really convinced by this, and instead of you're not happy by this sum to infinity, and you want to use the Sn formula, you can try that one out with a really high number. So you could use a r to the, let's say, I don't know, 10,000 minus 1, and r minus 1. And then you can substitute a and r into that as well. And you should get the same answer because it will converge extremely quickly. So your calculator, though it's not exactly the same, your calculator will give you the same answer to however many decimal places it will give you. Hoi, okay, right, example 25. Okay, example 25. Okay, so it says a geometric series converges to 8. So what does that mean? That means that our sum to infinity is equal to a minus over 1 minus r is equal to 8. The second term of the series is, so u2 is equal to 5 over 2 is equal to a times r to the n minus 1, so r to the 1, of course, because 2 is n. So we've got a times r. So there's our two formulas there. And essentially we've got a set of simultaneous equations which we can now solve again. You've got many different ways of doing that. You might be able to see that if you divide one by the other, that the a is going to cancel. So say, for example, we did 2 divided by 1, then you're going to get AR divided by A over 1 minus R. Okay, and that's equal to 8. No, it's not. It's equal to minus 2.5 divided by 8. This is perhaps a little bit messy and a bit tricky for you to sort out, but that will cancel there, and you'll be left with R divided by minus R. No, that's not true. 1 over 1 minus R. That's kind of nasty, okay, but that's the same as dividing by a fraction is the same as timesing by its reciprocal. You'll end up with 1 minus R. Maybe there was a neater way of doing that, I don't know. And likewise, you can work this one out as well. And then it looks like you've got a quadratic which you can solve. So expand the left-hand side, create a 0 by taking this thing to the other side, and then you can solve a quadratic. Okay, that's one way of doing it. Another way of doing it would be to maybe a nicer way of doing this would actually be to say a equals minus 2.5 divided by r, and we can substitute that into here, and we can times the 8 by this side, times by the r, and so on. Okay, but you should be able to deal with the algebra of that situation. The setup is the difficult thing, and then the sort of playing around a bit is the thing which hopefully you enjoy if you are an HL student. Okay, is that it? Is that it? That is it. Okay, right, I'm going to do a little extra for you here. Bit of a Billy bonus. And let's go to Excel. And I'm going to make, okay, right. There's my wife, by the way. That's the Norfolk coastline. Okay, let's zoom in a little bit here. Okay, and so what I'm going to do is I'm going to just put A in here and R in here, and these are two things I can change. So let's just pin that there. Let's put in, so two numbers here that I can change. Let's make this one an orange number. Okay, now I'm going to put in a sequence for UN, a geometric sequence. I can use a subscript here, probably just being a bit lazy. Okay, subscripts are, where are they? Subscript. Okay, right, so I've got that. Okay, right, and let's change this to SN here as well. Capital SN, like so. Okay, and let's just cut those, put them here. Put N in here, right? So Excel's pretty cool. So if I put in 1, 2, 3, now you can just make this a bit smaller. If you go to the corner there, you can drag this along. And in fact, let's just make some of these smaller. Okay, so let's just, 20 terms will do. Okay, make it a bit bigger again. Okay, so UN in this case is going to be, remember the formula for a geometric sequence we get is A. So this is going to be times by whatever's in here. A times by R to the power of n minus 1. So n is up here, n minus 1. That's just the UN formula which we have. Now, there's no numbers in there, so let's just put, I don't know, let's put in 1, 2. Okay, so that's, by the way, that's just going to give us the powers of 2. Right? If I pull that on across, get powers of 2. Should do. Oh, no, it isn't, because I'm being dumb, because I didn't fix anything. So in Excel, if I want to fix something, then I would put in, I would say I need to fix this each time. I would put in a dollar sign here and a dollar sign there as well. Now that fixes it, but I don't want to fix the C5 because that's going to change each time. N is going to change, but the A and the R is going to remain the same. So now we have our powers of 2, and obviously they get too big for the squares over here. Okay, and SN, the formula for SN, remember, is, so its formula for this is, let's put some brackets around, we've got A times brackets R to the power of N, and it's here, minus 1, close brackets again, divided by, open brackets, R minus 1. Okay, right. I'm going to need, of course, to fix certain things. So I'm going to fix these squares. I'm not going to fix the C5 because I want that to change. Okay, so this is going to give me my sum formula now. And so my sum formula, if I drag this across, these numbers here. So the 3 comes from the 1 plus the 2. The 7 comes from the 1 plus the 2 plus the 4. Now, there's another way of doing this. I could have done this. I could have said this is equal to the sum of this to the same number. Seems a bit strange, but if I fix the first number and leave the other number unfixed, copy and paste these ones across. There we go. I get, oh, why am I not getting the same numbers? Sum, what's going on there? Sum of C6. What am I doing here? Why has this changed? This should be the sum of C6. I used the wrong one, didn't I? It's the sum of C6. What am I doing there? Let's just get rid of that for a second. You get the idea of this. I'm doing the sum of, I probably clicked on the wrong thing. This to itself. Okay, so that's done. And then that's, for some reason that took C5, don't know why. Okay, right, so there's the same numbers there. So that's basically saying C6 to C6, C6 to D6, and it's changing each time as I drag across to E6 and so on. So it's the same. I'm just saying add these two, add these three, add these, cumulative score here. Right, but seeing as it's the same, it's pretty boring, so let's get rid of that. Now what I'm going to do is, what I can do is I can change these numbers at the start. So if I change this to 1.1, we can see that the common ratio is now 1.1. In fact, that should be 1.21 there. Like, for example, you can see that this is 11, you square it, you get 1.21, but it's not putting it in, there's not enough spaces for it to show. Okay, and anyway, you get the idea. So let's just make this a bit smaller. And let's now put in, let's get rid of that for a second. Let's insert, this is where it becomes kind of cool. Let's insert a chart. What should we insert? Maybe let's put in this. Let's check that out. But that's done as well because I haven't actually suggested anything to put in. So here we go. Let's put in these two things here into our chart. So insert. And here we go. Let's do it like this. So there's our chart. Let's get rid of the title. I want that. And okay, so there's the chart. So, let's make it a bit bigger. Let's put it over to the side here a bit. All right, okay, so what we can do is see that if we can see that UN is increasing exponentially, but SN is increasing even more exponentially. If we just got rid of that, then it will rescale it and it will look like the same exponential, in fact. But obviously, SN is much, much bigger as we go on. Okay, now if I change R to 2, again, it will look like all of these terms are completely flat, but that's simply because, it's just going off the scale at the end and showing doubling each time. It's like the reverse of that is showing halving each time as we go backwards. Halving each of these things. Halving this height becomes extremely small. So there is the same exponential graph going on there. It's just you can't really see it here because the common ratio is so high. Right, so if I take the common ratio down to, let's say, 0.9, oh, a bit different, right? So this time we can see that the sequence is converging. And likewise, the sum of these terms are converging as well. Now, that's obviously curving upwards, and this is curving downwards. Now, the sum of these terms here are converging to 0. In other words, there's an asymptote at 0 here. Whereas these ones are converging to the sum to infinity. And to find out what that is, it looks like it's around 9. But we could carry on if I took this a bit further here. Okay, let's just take that. Okay, let's take that further. I think, no, it's not taking it further on the graph, but we could. But you could see what it converges to, but we can also see here. You can see it is converging to 10, in fact. Okay, so it's actually converging to this line of 10 at the top. Okay, but we can find that out by doing A divided by 1 minus R. And that will give us what it's converging to as well. Okay, well, let's just see what happens when we put in a 2 here for A. It looks exactly the same. All you've done is scaled the axis. Let's just check that one out again. In this case, the y-axis went up to 10. In this case, y-axis now goes up to 20. So that's the sum to our infinity there for this convergent sequence. Now, if I go to minus 0.9, now that's really cool, right? So this means that we're oscillating each time. So each time our terms are going from positive to negative. Okay, now the sum of these stays positive, in fact. It stays positive because that first term was so large in comparison to the next term. So when we added this height to this height, we get a height of a bit more than 0. So that's kind of cool, I think. But you can see these converge, but they kind of oscillate to the whatever they're converging to. Remember, the blue line, the UN, the geometric sequence is converging to 0, whereas the sum is converging to the sum to infinity there. Okay, well, I think I'll leave it there for the time being. This might be something that you want to try and do yourself. If you want, try and just challenge yourself to see if you can remember what happened there. And yeah, this is kind of useful potentially for your IAs later on. be able to have these kind of skills with Excel. Okay, guys. Well, thank you very much for listening. I know that's really long. Hopefully, you've had several cups of tea in between. And maybe you skipped some of the questions because they were simply too easy. I don't know. You've got the exercise to do now, and as ever, I recommend the Oxford book. This is the PDF, but you should all have bought the Oxford book, and you should have got these questions here. Probably got a few of them. There's 15 questions there. I suggest you try and do all of those questions. Right, well, we have done 3 exercises in this book. Great, I'll do 1D later. Thank you very much, guys. I'll see you later.